Let's talk about the equation of radiative transfer, a little bit about light, and then about the equation of radiative transfer, which really is quite similar to radiation heat transfer. It's just we'll use slightly different nomenclature, and that will lead to slightly different forms for the expressions. Although there are people who do calculations on radiation in flames, all done with the equation of radiative transfer. Like the first name that comes to mind is a guy named Visconti at Purdue. They use nearly exactly the same formalism, except that they include things like soot in the formalism, and we won't, because we're mostly talking about spectroscopy. So first I'm going to talk about light, and then we'll talk about the equation of radiative transfer, and we'll end up on rate equations. So we're going to talk about some optical concepts that are important for diagnostics, and then we're going to show how you can perform calculation on diagnostics from a classical viewpoint. We're going to talk more about absorption and fluorescence, because we can use the same formalism to talk about chemiluminescence or, like I said, soot, for example. We won't talk about that, but this same formalism can include those if you wish. So the first point is that light is an electromagnetic wave, and in the next lecture we'll talk about that in detail. But the waves are characterized by a spectrum. So I'm sure you've seen this picture before where that goes to higher frequency, in other words bluer light, shorter wavelengths. In the visible we have from about 400 up to 700. You can actually see past 700 if you have an intense enough laser. Titanium sapphire lasers, for example, are at around 800 nanometers, and you can see that with you on a business card, but it's because it's such an intense laser. And then anyway, over at longer wavelengths you get infrared. There's a lot of molecular spectroscopy done there, and then up here is the ultraviolet. So when we talk about light, we talk about its wavelength in nanometers. I'm sure you know what the wavelength of this thing's dying on me. I'll use this one. Well, that one's dying on me too. Oh, that's great. Let's see. I know what I'll do. I'll do this silly thing I do sometimes. Oh yeah, thanks. Actually, now that I've got this, I have to tell you, I'm one of the very first people ever to use a laser to give a presentation. I developed this Q-switch diode pumped YAG laser when I was at Spectrophysics, and it was small enough that you could hold it in your hand. It had a fiber optic, had frequency doubler and everything, and I did this. That was a dangerous laser to be doing that with, but I did it. Thank you. All right. So anyway, light has a wavelength, lambda. I'm sure you know what the wavelength of a wave is. It's just the distance between the crests. And a frequency, nu, in hertz. Okay, and nu is related to lambda by this expression, u over lambda, where u is the speed of light in the material. And just as an aside, spectroscopists often use wave numbers, which would be nu over c. That's the speed of light in vacuum. And the wave numbers are given in inverse centimeters. Okay, that was the speed in material. The speed in a material is given by the speed of light in vacuum divided by the index of refraction, the material index of refraction, and that's what causes light to be steered by a lens, for example. So nu is a constant because energy is conserved, right? E equals h nu. You can't just suddenly change energy if you're going to enter a different gas or something like that, right? So nu is equal to u over lambda. It's equal to c over lambda naught, which is the wavelength in vacuum. So as light passes through various materials, you'll change the speed and you will change the wavelength, okay, depending on the index of the material. But the frequency doesn't change. And that's just something that sometimes people are confused by. There's also bandwidths to light. Light is never actually just one frequency. It always has bandwidth. And you can describe the bandwidth in terms of frequency or wavelength, and you just take a derivative, and some people, I think, haven't noticed that's how you do that. And the negative sign doesn't really matter because we're just talking about the width of the feature. You can describe light two different ways. Actually, you can describe it three different ways, but we're not going to talk about quantum optics here, so we'll talk about two different ways. There's classical optics. Okay, if you took an optics class where you learned about ray tracing and that kind of thing, how do you go from an object plane to an image plane with a lens, for example, that kind of stuff, that would be classical optics. And really what you focused on was the redirection of light. Those rays of light represent energy flow. But for most optics calculations, we didn't really worry about how much energy there was, because what we really cared about was how much will I magnify the image or something like that. Really what we cared about was more of a spatial thing than it was an energy intensity thing. But you actually were tracing energy when you did that. So classical optics has to do with energy conservation, although it was hidden. And we actually represent energy conservation by the equation of radiative transfer. So what I'm trying to say is the ERT is like a subset, kind of a niche of the classical optics world. It's not a physical optics question. So for diagnostics, we use classical optics. Whenever we do imaging, of course, we worry about how much am I going to magnify the image, how big is the blur spot, how good will the spatial resolution be, all that kind of stuff. And then we use the equation of radiative transfer also, so we can understand techniques like absorption, fluorescence, PIV, and so on. Then there's the subject of physical optics, and that describes electromagnetic waves with the wave equation often. And we have to use that formalism to talk about interference or diffraction or the ultimate image resolution of an imaging system. How do lasers work, that kind of thing. Or even that DFWM I just talked about, that interference pattern, that classical description of DFWM can be written out in terms of physical optics. So you use physical optics for laser beam propagation, interferometry, including phase Doppler interferometry. Somebody was just asking about laser Doppler anemometry, which is quite similar to phase Doppler interferometry. Those cross two beams in space cause an interference fringe, just like I described, except that it's not absorbed. Particle scattering, holography, for example, nonlinear optics, all those things. Physical optics and classical optics are parallel formalisms, and they're linked by the Poynting theorem, where you can turn the electric field strength into irradiance, and you can get the same answer. Okay, so they don't disagree with each other. They are not different answers. You will get the same answer if you try to analyze the same problem. They're just two different ways to handle the problem. Sometimes it makes more sense. A lot of times it's just a lot easier to use the equation of radiative transfer, and if you can do it, why not? Sometimes you have to use physical optics. Don't feel like you suddenly abandoned everything that you understood in classical optics. It's the same thing. It's just a different way to handle it. They handle different aspects of the problem. So let's have some definitions. I use the word irradiance. That's the power per unit area in, like this laser beam, for example. J would be called the radiance. This is similar to radiation heat transfer, where it's power per unit area per sterradian. Okay? Where, if you haven't seen this before, a sterradian is like a two-dimensional version of a radian in angle, or radian angle, right? So if you look at this picture here, it's this side times that side, where this is r sine theta d phi, right? Where that's theta and phi is in this direction. And then we have to worry about that side, which is rd theta. So that is going to be the area defined by those divided by the distance along r squared, because the units of A are square distance, right? So instead of a differential distance in an arc divided by the radius, it's the differential area divided by the radius squared. Rho is the energy density, or energy per unit volume, joules per cubic meter. And E sub P is the energy per photon. Okay, energy per photon is h nu, where h is Planck's constant given by this. Now on a per unit bandwidth basis, sometimes when we talk about stuff where we have to worry about how does something interact with different wavelengths of light, light always has bandwidth, so sometimes it has to be done on a per unit bandwidth basis. I don't know about you, but sometimes I get kind of annoyed with, okay, now why are we introducing more complication? It's because we have to sometimes. Light has bandwidth. Sometimes you can avoid worrying about it, sometimes you can't. So this is power per unit area per unit bandwidth given by those units. There's a spectral irradiance as well. Spectral energy density, joules per cubic meter per hertz. And you can relate those to each other. The spectral irradiance is equal to the density times the rate at which it, if you think about it, it's density as it's moving along, right? Density times the speed at which it moves. The radiance is equal to that over the solid angle. The irradiance is equal to the spectral irradiance integrated over the different wavelengths that are available, whatever the interaction might be. And then J is given by a similar expression. The number of photons per unit volume is then given by this. Those things, what I'm going to do is skip along through an entire long chapter in my book. So I realize sometimes I am giving you a parachute formula, but there's a lot. And those are just definitions. So the equation of radiative transfer now, we're going to use those definitions in terms that we write here. The ERT is just conservation of energy, and we do the same thing you would do in fluid mechanics or heat transfer or diffusion or something like that. You draw a little differential volume in space and you add up what goes in and what goes out. That's it. So the rate of change of energy inside the control volume is equal to the rate at which it enters divided by the minus the rate at which it leaves, plus energy creation terms minus loss terms. That's all it is. You've seen that lots of times, I think. For the creation and loss terms, we're going to assume that the interactions are spectroscopic. Like I said, you could also talk about soot radiation, right? Then you'd have to worry about the creation of soot and how does it radiate and so on, and we aren't going to do that here. We're just going to look at spectroscopic terms. So we did this before. We're going to say spectroscopic interactions are occurring between two allowed quantum levels. It's very common to assume a two-level system, certainly to get started with. These things aren't really two-level systems, but you usually begin with that concept to describe how these things work. So the spectroscopic version of the ERT is this one, where we're looking at the rate of change of energy within the volume times the divergence of the energy flow as it goes through the volume, and that has to equal source and sink terms, which are given by these. That's all that is. It's the same as energy conservation in other expressions, just written with different constitutive relationships. That's all. So here, n sub n is the number density of atoms or molecules in the upper energy level. N sub m over there is equal to the number in the lower energy level. A is the Einstein coefficient for spontaneous emission, given right there. So this term describes spontaneous emission from molecules within the volume, and that's the one that produces an LIF signal. Of course, you have to create, when you're doing LIF, you have to create molecules in that level, but once they're in that level, the fluorescence emission is controlled by that term. BNM is the Einstein coefficient for stimulated emission, given by that, the number in that level times this rate at which it will depopulate. BMN is the Einstein coefficient for absorption, okay, going from M to N. And then this Y sub nu is the interaction line shape function in 1 over hertz. We haven't talked about that yet, but I showed you that picture where there wasn't like a spike in frequency space. It had some spectral bandwidth to it, and that's what Y describes. Because these are spectral terms. Rho sub nu is a spectral term. That's why these things exist there. So these terms associated with the Einstein coefficients are sources and sinks for optical energy. And originally, these expressions were written before all the arguments and fistfights and everything happened over quantum mechanics. And this was kind of a definition of those coefficients. So the line-shaped function can look like this. And the point is that transitions between M and N don't happen at just one precise frequency. There is some bandwidth to the phenomenon. So here's the center frequency. You can be just slightly off and still cause a a transition, although it's not as strong as it would be if you were on line center. And we'll talk about why later on. These line shape functions that we use are all normalized, so the integral of this y sub nu over all frequencies should be equal to 1. So it's a fraction. Y sub nu describes the fraction of the total response that you'll get here, for example. And because this has line width, you can't have a fractional absorption of 1 at center line because the entire integrated absorption has got to be equal to 1. The line shape function has to be equal to 1. That's why this goes to, what is it, 0.6 or something like that. It's just a cartoon I drew. We'll talk about that a lot more later on. Okay, if we want to take that expression and turn it into something that we use, which is what we're going to do next, we have to make some assumptions. So it's very common to assume steady state. For example, with laser-induced fluorescence, I showed you that S sub f is equal to all this stuff. That assumes steady state, which seems kind of weird when you consider that it's a 10 nanosecond laser pulse that's going to do this. But relative to the speeds at which a molecule can cycle through populations, 10 nanoseconds is pretty long, and it's okay to assume steady state, unless you want to worry about the leading edge of the pulse or something like that. So we can assume that the rate of change with time goes to 0. And then it turns out that the d nu terms cancel out of that equation. Let's also assume that light is traveling along some optic axis. And that's easy to do with a laser beam, right? You just, the center of the laser beam defines an optic axis, let's say. It has a relatively small solid angle. So you can say that the rate of change with off-axis terms is fairly low. And recall that we said j sub nu is equal to c, the speed at which this is moving, times the volume of energy that's in the thing that's moving, divided by the solid angle. So then we can turn the spectroscopic equation of radiative transfer into this. So you just take that equation number 1 and do these things to it, and you get this. The rate at which this is evolving along z now, we got rid of the dependence on the other axes. Is equal to these terms. There's that's a loss term, and that's a source term, and that's a loss term as well. Or yeah. Now we're going to define a few terms, and that's because we don't really need to define these terms. You could just use what I just wrote. But what I want to do is show it to you in the form that you'll find in articles. Okay, and to get in the form that's in articles, you have to define some terms and manipulate the answer a little bit. So we define a volume emission coefficient per sterradian epsilon, which is really just that term that contained the Einstein coefficient, right? That's just bundled all together, that's all. And a volume absorption coefficient, which was this term, which had to do with excitation. Let's go back a bit. If you look here, this term has got a J in it, stimulated by the laser beam if we're using a laser, right? This one doesn't. Okay, so that's why we're doing it this way. This one is a stimulated term. You require light to be there to make these things happen, where with this one you don't actually have to do that. In fact, chemiluminescence, you could have a chemical reaction that populates the upper level and it will give off light, right? You don't actually have to have a laser beam there. So that's why we did it this way. So this is the term that will interact with the light. This one won't. So the spectroscopic ERT becomes something fairly simple looking just because we just bundled everything into those two terms. So we can also define a source function, which is epsilon divided by kappa. Why did we do that? Because later on it'll be convenient to do it that way. And then there's an optical depth, which you have probably heard of before. Tau sub nu is used in this formalism. It's equal to the absorption coefficient integrated across some path length from 0 to L. Okay? Optical depth is how much light gets through, okay, basically. What's interesting is this formalism can reproduce Planck's blackbody distribution if you make it optically thick. So if you take a collection of spectroscopic lines, like water, water's everywhere. You just fill this thing with all the spectroscopy of all the molecules that are in this surface, for example, lots and lots of discrete lines, and you add optical depths because these things all have high optical depths. you can recreate the Planck blackbody distribution function. The blackbody distribution function is the same thing as this. And in my book, I show how that works. So optical depth has to do with, can you see those details through this thing? Or is it so thick that everything turns into the Planck distribution? You can leave the ERT that way, but people, and like I said, I'm trying to explain to you where these things came from that you see in journals. Researchers often assume the medium is homogeneous, so there's no dependence on Z now. To get the expression that we use in diagnostics, we assume it's homogeneous going forward, but that assumption can be seriously in error in a flame if it's non-premixed. Or even if you're looking through the flame front, even in a premixed flame, it can be seriously in error. But if we assume homogeneity, these things don't depend on distance anymore. We can say that kappa was constant across L, and so the optical depth is just that. So the spectroscopic ERT is integrated across DZ, and you get this, where this is the radiance, the spectral radiance. This is an absorption term, and you can see that's beginning to look familiar. That's beginning to look like Beer's law, and this is an emission term. And this is why we defined the source function that way. It looks a little funny because there was a kappa and there was an epsilon, and now we suddenly have the source function, but it's really just algebra. It's a bunch of steps I'm skipping because it takes too long. So you see you end up with these two terms. So if the medium is emitting light, like chemiluminescence, or maybe we're getting light from LIF, and there's no light source being absorbed in that same direction that we're looking, you can write it this way. So that's just an emission description. If the optical depth is small, you can linearize that expression, and that just tells you that the emission is given by that. So if you could actually model the chemistry that produces chemiluminescence, for example, you could model the source terms and model the chemiluminescence as a function of position. It becomes very complicated, though. 1 over 4 pi is there because this is on a per unit solid angle basis, okay? If you want to convert to a radiance, you multiply by the solid angle that you're using. What's the solid angle that you're using? Well, if here's my flame right here, it's really just the area of the lens, the collection of the lens, the area that the lens can collect from divided by the distance squared. That's it. So these things are all related to something that's physical. If the medium is not emitting, but it's illuminated by a light source that can be absorbed, you can write it this way, and that's a form of Beer's law. Usually, the solid angle doesn't change with distance like if we're doing diode laser absorption spectroscopy, right? You're going to have a detector over here that's collecting a fixed solid angle. It's not changing with position. So you can get rid of that and write it in terms of irradiance that way. And that's the most common form of the Beerlambert law. If it's optically thin, okay, so tau is not very big, and the excited state is not populated, okay, by anything, which is sometimes the case, you can get an expression like this. And I bring that up because you may run into that sometimes. That was an expression people used a long time ago before we had computing power. I go back to the days when people computed with punch cards. So there was a time when there wasn't a lot of computing power, and people would do this as a way to simplify the expression, make it easier to calculate what was happening. But nobody uses that anymore. You might see it, though. Here's the effect of optical depth. I just thought I'd show that to you. This is what it really means. It's equal to this if we assume that the field is uniform. And here's transmission tau. That's equal to I after I that comes out of the thing divided by I that was coming into the thing, right? I L over I0 as a function of frequency. And I've shown you a picture like this before, but as we make optical depths go up, this thing becomes what's called optically thick. Basically, transmission goes to 0 at line center, and you don't have the nice, clean line shape function that you had before. And in terms of emission, the same thing happens, right? So this is actually that emission coefficient S as a function of wavelength or frequency. And you can see what's happening. As it goes optically thick, that starts to hit the ceiling and spread out sideways. That's what produces the Planck black body distribution function. It goes optically thick, everything hits the Planck level. In fact, in the old days, you remember that when you studied heat transfer, you talked about the emissivity of a surface. In the old days, when they did spectroscopy using that crude expression I used before, they often wrote it in terms of a spectral emissivity. Everything was written in terms of an emissivity, and they did spectra that way. So the two things are the same thing, just the Planck distribution is for a very optically thick medium, where when we study flames, it's not so optically thick. We hope, or you'd never be able to get your signal out. So I don't know if you noticed, but the equation of radiative transfer had relationships for the rate of exchange of populations. There were those Einstein coefficients, and we just sort of said, okay, they're in there, and then we hid them in epsilon and kappa, right? But those n times the Einstein coefficient is actually a rate, right? So you can write rate expressions almost like extremely crude chemical kinetics. So let's go back to that original formalism, right? There they were, those expressions there. Now we're going to, now I've included this Q, which is the collisional rate at which we remove population. Okay, thank you. He's a friend of mine. Ola is his dog. Should we talk to him? That'd freak somebody out, wouldn't it? Anyway, Q is the collisional quenching rate. We didn't have that before. Okay, so now we can write it this way, where I've just rearranged things a little bit. This is dN dt, that's dNm, dNn. Okay, so that's the excited state population change, that's the lower state population change. Where if you look at it this way, this is going to be, this is the Einstein rate for excitation, right? It's going to be a minus because we're going to depopulate. Those expressions help define the Einstein coefficients, but you can actually calculate those several different ways using quantum mechanics now. Quantum mechanics also is not inconsistent with these other expressions. So we can make the following definitions. There's a stimulated absorption rate, which is WMN. Just these terms put together. There's the irradiance that is driving the absorption. Here's the stimulated emission rate. So then we can just write it this way. So there's emission and absorption written in there. So the line shape is normalized, which is why it disappeared from the ANM term. So finally, we just get this. Populations times rate coefficients. And that's how this changes with time. So for spontaneous emission, for example, we can just talk about, now we're not talking about depopulating level M, because that's done some other way. Okay, if we have chemiluminescence, for example, the excited state was created chemically, not optically. So we're not going to talk about optical depopulation of the lower state. Something chemical happened. So somehow magically an excited state appeared. How is it going to give off light? Well, it's going to give off light by changing the population of the excited state. The population will lose population and give off light. So absorption and spontaneous emission probably seem fairly clear. We talked about Beer's law. We've just talked about spontaneous emission. Stimulated emission is a little bit stranger, so let's walk through that. Here's energy, and I'm just showing you energy levels in different processes. And so we start at number 1. Let's say the molecule is in the upper energy level N. Okay, it can end up there several different ways. You could pump it up there with a laser. And this actually does happen during laser diagnostics. Stimulated emission can happen during laser diagnostics. Sometimes it actually is a significant term. Most of the time it's not. But somehow we got a molecule in an upper energy level, okay? And then somehow a photon comes along at exactly nu nm. It just happens that that's the case, okay? What it can do is it'll interact with this excited state and it will stimulate a transition down to m. It will cause that transition to happen. Okay, and what you get are 2 photons, both at the same wavelength. So we send this down to the lower energy level, we harvest a photon, and you get 2 of them out of 1, and that produces a second photon, and those are coherent with each other. We'll talk a little bit more about coherence when we talk about the wave equation, but that's actually where you get laser gain. That's why you get amplification in the laser cavity. You create molecules in that state, and then you rely upon stimulated emission to create the gain at the wavelength of the laser. That, when we do laser diagnostics, like I said, it's extremely rare that that would actually be a noticeable thing. So most of the time we neglect it. Let's talk about saturation. In the old days, people really liked the idea of saturated fluorescence. And you can describe, you can write an expression for saturation as well using these rate equations. So when we do laser absorption, for example, we usually neglect the stimulated emission terms because it's the ground state that you're pumping, right? And that has a huge population, much, much bigger than the excited state. But as the energy of the laser beam goes up, this grows, okay? You can start to like flood the upper state. To analyze that, we're going to make it simple and assume that the energy density is so broad spectrally that we don't have to worry about spectral dependence. That's an assumption you sometimes make. Like, for example, if you have an absorption line, an extremely broadband laser, we just say, okay, we don't have to worry about line shape. The whole signal is integrated across the whole thing. You don't have to worry about a spectral overlap integral or anything like that. It just falls out. So as integrals go to 1, and we'll get rid of that. So it's a two-level system, which isn't really realistic, but that's what we're dealing with. So we say, okay, this is mass conservation. Somehow those two have to be equal to some total number density. If we depopulate M, then it's all going to have to end up in N. So if N reaches its maximum, the system is called saturated. So we just depopulate M until it gets to N. And what happens there is that because there's so much excited state population, stimulated emission starts to take over. Spontaneous emission is no longer so important. The irradiance of the laser beam is going to start to stimulate a lot of population change down to the lower state, and you start to drive this thing in a cycle. Okay? So now when that happens, there's really no dependence on time anymore, because you've basically filled the excited state as far as you can. And it's just going to be cycling back and forth. Nothing's going to look like it's changing with time now. So we can get rid of the time dependence, and we got that. Now we use conservation of mass to remove n sub n, and we get this expression here. You recall that we wrote that expression for I, so we can write this way, where the saturation irradiance is given by that term there. And that's why I threw Q back in, because often in laser diagnostics, people talk about saturation, and you have to have the Q term in there as well to describe saturation, because saturation is fighting Q. Saturation, to saturate the transition, you're not just fighting spontaneous emission, you're also fighting Q. But if you can pull it off, if you can get I well above I saturation, you share the populations. This is just a two-level system, of course, which isn't really realistic, but you actually share the two populations between the two, cycling around, half in the excited state, half in the lower state. Has anybody here ever tried saturated fluorescence or thought about trying saturated fluorescence? Was it a success? Then you must have done it right. Saturated fluorescence has got several problems. One of them is that the laser beam isn't a top hat. It looks like if this is the center line of the laser, you get a Gaussian distribution usually in the laser. Well, if this has these irradiance to saturate, this won't. So you have to be careful about how you collect the signal. You don't want to be collecting signal from places that aren't saturated. Okay? Then the other thing is the laser pulse itself in time looks like this. There's this photon explosion at the beginning where you get a really steep rise, and then this falls off exponentially, almost like cavity ring down. That tail is going to have a problem with saturation as well, and you have to figure out what to do about that. So most of these laser diagnostics have a lot of these details built into them where if you want to try one and you start running into trouble, it's because there's these trade secrets people have, right? And so if you start trying to do something and you're running into trouble, you should just contact one of us, because well, if they don't help you out, then ignore them and find somebody who will. So that's why saturation is not so easy to do. So what did you do it on? What molecule? OH. And was it a pulse YAG system or? Cool. That actually really simplifies your measurement. Anyway, don't confuse an optically thick situation with saturation. Those are two totally different things. But we've talked about them both in the same lecture, so don't confuse the two. So I'm going to start on physical optics and the wave equation. We can take a coffee break now, or we can start on it. What would you like to do? Okay, those who want to have a break, raise your hands. Okay, we'll start on it. And then about 10 after, we'll have another break. So I want to talk about Maxwell's equations and the wave equation, and then talk about interaction of light with matter. There's a classical formalism called the Lorentz atom, which I think is pretty cool, that actually has a lot of the physics we actually use built into it, even though it's a classical description, which is kind of neat. So we're going to talk about physical optics, and we're going to talk about propagation of electromagnetic waves and their interaction with matter, and a classic picture of the Lorentz atom. We have to understand physical optics if we want to understand nonlinear optics, or scattering, or diffraction, okay? Or also how we can couple light to quantum mechanics via the density matrix equations. If you want to talk about how light actually interacts with a quantum dipole in time, you have to use these things called the density matrix equations, and the semi-classical way to do it is to treat the light wave as a classical electromagnetic wave and the molecule as in quantum mechanics. And you get the same answer. We actually, in my book, we actually show how you can use the density matrix equations to get the classical description of the Einstein coefficient. So they're all the same thing. Light is an electromagnetic wave, so I like this little picture. Here's the electric field. E stands for the electric field, right? And it's a vector because it's polarized, it's called. You see those, the blue vectors, and that's the wavelength. And then this is the magnetic field B. Okay, we'll talk a little bit in a minute about why are those normal to each other, and they're both normal to propagation direction K. X-rays and microwaves are also electromagnetic waves. What's cool about this is there is a fixed electric permittivity and a magnetic permeability of free space, which is kind of neat. That allows the electric field the electromagnetic field to actually travel across the vacuum of space, which is why light from the sun reaches us. People used to argue, this was a long time ago, around 1900, they used to argue about this thing called a luminiferous ether. Was there a luminiferous ether out in space that would propagate a wave like an acoustic wave? Because they were used to acoustics, that requires the gas. And they couldn't believe that you didn't need something to propagate a light wave, but they finally realized that you can do it straight across outer space. So that allows the electric field and the magnetic field to propagate through free space. This was all. This was a really smart guy. There were like expressions in electromagnetism, but they weren't connected to each other. This guy figured out how they were connected and how to make them connected, and he's the one who figured out that that's light. That's what light is. There's some people in the history of science that just astound me because there was no way to prove this kind of stuff. You couldn't actually see it. You couldn't manipulate it. You just had to realize it in your head. Anyway, that's James Clerk Maxwell and his dog. That's in Edinburgh, this statue. It's at the end of George Street in Newtown, which I think is kind of cool. Usually there's people in some war on a horse, right? Instead, there's a scientist sitting there. And there's Maxwell's equations. Here they are. Now notice that these are written in MKS units, okay? So I'm telling you right now, that's what we're using. So there are three equations. They include expressions for the electric and the magnetic fields. This is the free charge current in space. That's the free charge density. We're going to make those go away because we're going to assume that in a flame they don't exist. This is where Maxwell was really, really smart. He realized that there had to be a rate of change of the electric field here looking almost like some kind of a current. And that was how he was able to unify these four expressions into an expression for the propagation of an electromagnetic wave. That was his big aha that made it possible to combine these four equations. I already told you about this. Be aware there's three different unit schemes, right? I'm telling you, we're doing this in MKSA units. We're going to make these assumptions that the optical interactions are all electronic, and that's typically what we do. Sometimes you'll hear about people doing spectroscopy on a forbidden transition, but it's a very weak thing. Sometimes there's actually a magnetic monopole that they're taking advantage of. And so very, very rarely there's actually a magnetic interaction, but that's very rare. And so in optics, we typically assume that everything happens with the electric field, not the magnetic field. The magnetic field just goes along for the ride. So all the things we describe in terms of an electric field. And we're going to assume that in a flame or someplace where we're making measurements that the free charge density and current are 0, because there's not a stream of, it's not a plasma or something like that. If it were a plasma, we'd have to worry about that. So if we apply vector calculus, and I'm going to take some shortcuts because we don't have time. If we apply some vector calculus to the Maxwell's equations, we get these two expressions for the electric and magnetic fields based upon these assumptions. Those are two wave equations, both of them. And they both have the speed of the waves given by this. What was really cool about this is that independent measurements of those two terms compared to the speed of light that was measured turned out to be that actually was correct. So those are waves. Okay, who was in Sebastian Candel's lecture this morning? Yeah, he's talking about waves too, right? Same formalism actually, exactly the same formalism. This is how you describe the propagation of a wave. So we're going to take the real part of this expression here, where this is an amplitude of the wave. In our case, the amplitude is a vector, okay? We take the exponential. This is really just sines and cosines, right? If we end up taking the real part, we're just going to get sines and cosines, but this is easy to manipulate. It's easier to manipulate this expression than sines and cosines. That's why we're doing it. So I, the imaginary number, times k dot r. K is going to be the wave vector. It points in a specific direction, the propagation direction of a particular wave front. Dotted onto r, the position vector, minus omega, which is the radial frequency times time. And B has got the same kind of expression. The magnitude of k is given by 2 pi over lambda, and omega is 2 pi times the frequency in hertz. So they're describing in a simple arrangement of plane waves, okay? And in fact, in my book, I explain why k dot r actually describes the motion of a plane wave, but we don't have time for that. So k is the direction that this plane wave is going in. You remember when I talked about DFWM, I talked about this collection of plane waves. Now I'm trying to show you a three-dimensional picture of the plane wave, okay? And what that means is that the electric field, it could be oscillating vertically like this, where maybe this is the peak and that's the trough in the electric field. Okay, that's why they're in different colors. And the magnetic field would be oscillating horizontally if that were the case. Now, for a laser beam, for example, we typically model this as an infinite plane wave, right? It goes out to infinity. But how can that possibly be true? Now you have infinite energy. No, the energy falls off in a Gaussian form, so it goes out to 0 in the wings. The wave equation is linear, so we can take equation 13 to form a basis set of solutions. We're going to sum up a whole bunch of a linear collection of those solutions with various values for these things. Okay, and you can combine those to form complex solutions to the wave equation. And in fact, there's an entire field called Fourier optics, where the far field diffraction expressions actually take Fourier transforms. And in holography, for example, these values of k, they're little vectors that stick out in different directions, little unit vectors sticking in different directions and so forth. Those are actually the spatial frequency components of an image. So a high spatial frequency component means a small thingy, and a small spatial frequency component, small frequency means a big thingy. And an image makes a collection out of all of those things. And what holography does is record those as a function of depth and position. So this concept of a plane wave is actually extremely powerful. It can tell you about imaging. It can tell you a lot of things. We won't go into so much detail here. So it's a very important building block for a lot of physical optics solutions. Well, if we plug equation 13, that wave equation, into equations 7 and 8, we get these two expressions. del dot E, or I'm sorry, the divergence of E is equal to this, goes to 0. So in other words, K dot E goes to 0, and so does K dot B go to 0. In other words, E and B are both normal to K, as I showed in that picture. Okay? So they're transverse waves. Now if we plug that into equation 9, we get this. So I'm skipping along. I'm sorry I'm moving it quickly, but I just want to show you that what that means is, since E is normal to K, E and B have to be normal to each other. That actually proves that picture I showed on the first page with the electric field oscillating vertically, a magnetic field oscillating horizontally, and all of it going in the direction of K. That's why that's the case. So they form a right-handed coordinate system. You note that we had these amplitude terms given by those. Those are actually vectors, and that's why I've been talking about this actually, this idea of a plane wave with orthogonal electric and magnetic fields. In optics, the direction of that electric field is called polarization. It's the polarization of the beam. And a lot of the things we do require that we understand what the polarization is and manipulate the polarization. And I think we'll stop there and take a break and then finish.